No lower, please.
Stop. Yeah. Go.
This week on Power Hour. Oh, sorry. Go ahead, Kisha.
Okay, so this week on we have with current Ryan Shripat. Take it away, Ryan.
Okay, guys. All right. So today's episode of Ryan Minutia is a loosely related collection of vignettes around the theme of electricity, electronics, electronic components, electronic repairs, and repair in general. So I am essentially presenting on things that I find interesting, and is something I kind of want other people to reduce the level of fear for and try to attempt on their own, especially in these times where remote learning is now the default rather than the exception. You want to be able to assist those around you who are less fortunate and who might not be able to afford new devices. You might be able to put forward some assistance there to help them out. So I'll be going a little bit fast because the time is limited, and you guys already cost me 4 minutes. If you want, I probably won't be monitoring the chat, but if you want, feel free to cut in any time with your audio questions. I have no problem. I can speak while I'm dealing with my things. Okay, so the first part that we're going to deal with here would be looking at the various components of a desktop computer. I know low hanging fruit for a lot of you. I don't want to say guys. There's low hanging fruit for a lot of you technical minded people, but I want to broaden the scope of it to allow other not so technically inclined people to be able to get comfortable with desktop computers and how they're built, because they're amazingly easy to repair, unlike laptops and Nooks and so on and so forth. They require a normal screwdriver to get into, easy to repair, easy for you to attempt, easy for you to learn and overcome your fear and try to help out as the case may be. So I have here a computer donated by a company. I'm not sure which camera is the best one to see, but we have here, this is a computer case, and the computer motherboard is inside of there with a smorgasbord of cables attached to it. So I'll just get some of these cables out of the way here. I've already unscrewed and undone most of the cables here. So I'll get this motherboard out. Now it's a very easy, simple process for taking motherboards out of a computer. Sorry, I'll speak to this camera instead. So it's actually a very easy process for getting components out of a desktop computer. As you can see, there's lots of space involved here. The important thing is where the power supply is on the bottom here. You don't wanna touch that too much, no? And probably try to unplug it before you go digging around inside of there. This power supply, he has things called capacitors. And Croatia, I have you on standby on speed dial here, so you can assist me if I started to shipping this. But you can get a nasty shock from one of these power supplies. Just keep your fingers out of the holes and the swirly bits, because there's also a fan in there, right? So that converts 110 volts AC from your mains into DC. So computers and digital equipment, most electronics use direct current, not alternating current. Alternating current is what comes from the plugs. DC current is what you get from batteries, and what computer power supplies convert into DC. All right, so I'll go ahead and take this motherboard out of here and give you a little tour of the components therein. Get that out of the way. All right, here's my pointer device here. So the biggest thing you can see on this motherboard, is a computer fan. The fan here. This fan is attached to something called a heat sink, which is used to soak heat away from the processor. Right. So I have another board here that I can show you. where you can more clearly see the processor here. This is actually one of my old boards. It has an AMD Phenom 2 processor. So this is what the processor looks like underneath your heatsink and fan. So the reason for the heatsink and the fan is that these processors tend to generate quite a lot of heat, and so the heatsink is essentially a metal block with pins that soak up the heat from the processor away from the processor, and the fan is used to radiate that heat away from the heatsink itself to increase the thermal capacity of the heatsink. All right, so I can just show you this processor here. Just open that thingamabob. Sorry, I only have I have 0 thumbs today. Sorry, I had a little accident where I chopped off the top of my finger. But this is what the processor looks like. It only goes in one way. Generally speaking, if you're going to repair your neighbor's computer, you're not going to be dealing with the processor. Most likely it's something else. So let's go ahead and continue looking at our initial motherboard. So we have here our fan, heatsink, processor underneath there. On the back, you'll see the back. Sorry, let me switch screens. Make it clearer. I have the wrong screen all the time. That's all. Let's go one more time. So first technical issue, guys. That's fine. We shall overcome. Okay, here we go. All right. So we have this on the right view. So right, processor. So let's talk about that. Right. If you look at the back here, you'll notice all the ports. These should be familiar to you. Keyboard, mouse, VGA output for connection to your monitor, your USB ports, Ethernet port over here, audio outputs. Different motherboards have different I/O ports or input/output ports, depending on the motherboard, and so that's part most familiar with you, right? Over here, we're going to be talking a lot about power today and electricity. This is where the DC current comes in from the computer power supply. That comes in here and that provides power to most of the motherboard components. The CPU itself, he has his own power socket, so he also gets power directly from the power supply and not through this guy here. We have some expansion slots here. The PCI, I think this is PCI Express port here. This is where typically you plug in a card, a graphics card like this guy here. So again, this is a graphics card providing VGA and DVI output here. And this will generally just plug right inside it there, easy peasy, right? I'm not going to complicate this build here at all. So to show you how simple this is, we're just going to, sometimes when you have a computer set up inside of a case, if the first thing you want to do in terms of a computer that is not working, you want to try and figure out exactly what is the cause of the problem. So you try to eliminate as much of the complexity as possible. You pull out the hard drive. The hard drive generally go in through here. There are more modern connections, but we'll just look at these for now. So the hard drive generally goes in here there's a power and a data cable. If you unplug the hard drives, you eliminate any possibility that the hard drives are causing any issue with the system. If there's RAM in the system, well, there is RAM on the system, you take the RAM out, you blow on the contacts, probably not good advice for a new machine, but whatever, it's an old non-working machine, so you could probably blow on the contacts or clean contacts in some way or the other, slot it back in. Change the slot that the RAM is in. You switch things around. The idea is that you try known working parts on the system, but if you are not a computer repair person or you don't happen to have like a million computers in your spare room like me, then you're gonna be hard pressed to find spare parts. So you're gonna have to work with what you have, right? So you unplug everything. If you have onboard graphics like this board provides, and you pull out the graphics card and try this guy instead. And if all of that doesn't work while you're inside of the computer, what you can do, so other problems can manifest themselves. So for example, if the case or the IO shield of the computer got in contact with one of these, with some of the positive power pins on here, that could cause a short, which would cause the power supply to decide, hey, I'm not going to give you any more power, and computer won't boot at all. So to further in the spirit of eliminating all other possibilities, you want to take out this motherboard from the case. So you could take this motherboard out of the case. You could first visually examine it. You wanna have either anti-static bracelet or keep touching ground. So I have a nice exposed piece of metal here. I keep touching the ground myself because static could be dangerous to various components on the board. Or you can do what the guy from The Verge did and wear What Would Jesus Do bracelet, and that would quite probably protect you from the dangers of electrostatic discharge. Yeah, so we move on here now. So what we're gonna do, we're gonna actually, so having pulled out the motherboard from the case, well, how do we even go about dealing with this? Well, I mean, first thing you can do once you're protected, of course, is that you check for any burn marks, any obvious burn marks. If there are no burn marks there, well, that's the extent of your visual examination. Now we can try to power this guy on. So one of the sets of pins that I neglected to point out before would have been the front case panel pins over here. So these pins, all cases come with plugs connected to switches and LEDs that connect to this here in a standard configuration. The things that plug in here would be the power switch, the power LED, the reset switch possibly, and the hard drive LED, the hard drive activity light. So those four things could get plugged into here, right? So since we've unplugged that, I'm not gonna chuck this back into the case just to turn it on to see what happens. So what we're gonna do now, we're gonna try to plug this guy in and see what happens. So I'll put aside my screwdriver there and grab one of these guys here. So as mentioned before, this is your computer power supply. You'd have seen the back end of it. This is usually the back end where you oh my God, this is dusty. Yes, so this is the back end of it, where your mains power comes in and comes through here, converts the AC power into DC. So let's try to plug this guy back together and let's see what we can do here. So let's go ahead here. This is a 24-pin ATX connector, and let's get this guy inside here. Any questions, you guys feel free to comment. I'll respond while I am doing this. So I'm kind of abusing this board.
Hey Ryan, you hear me fine?
Yep.
Was this while kind of refreshing yourself on this stuff, I guess over the last year, like since there was a big push during the pandemic,
Yeah.
did you feel a sense of nostalgia, like a sort of a return to maybe your roots, as it were, in terms of IT and computing?
Well, I first got into programming because I was interested in hardware. I thought it was amazing to be able to write a line of code and say beep in a basic program and cause the computer speaker to beep. So in a sense, it is in fact a return to basics. I feel I'm missing a word there. But yeah, it certainly sparked an interest. It re-sparked an interest in me. So as mentioned before, this power supply is going to provide power to our motherboard. The CPU, as again mentioned before, he requires his own power from the power supply. So we're going to plug that guy in here, right? And what else do we have? Well, most of these guys are for hooking up hard drives and so on. It's just a gaggle of ketchup and mustard cables, as they call it. We have a loose guy here. This is actually the CPU fan plug. So this provides power. Couple of things with this plug here. So you'll notice the colors. You may or may not notice the colors. But there's a red cable, there's a black cable, there's a blue cable, and there's a yellow cable. The black is obviously ground. Red is, I think it's 12 volt power, either 12 or 5 volts power. And the yellow is used to, I think the blue one is PWM. That's pulse width modulation, I think, but I think it's used to control the speed of the fan. Like if the CPU is under heavy load, it might ramp up the speed to the speed of the fan to compensate for the extra heat. And the yellow cable reports the speed of the fan back to the system. So let's go ahead and plug this guy back in. For some reason or the other, I'm a little bit fascinated with fans, and I don't know, find them cool. All right, so what we're missing from this board?
So Ryan, you're a real fanboy?
I'll let that joke blow away on its own. All right, so what we're missing from this board, guys? Anybody? Do we have all that we need to start this computer?
No, we're missing RAM. How many pieces do you have?
Okay, cool. Let's get some RAM then. Wow, we just happen to have some RAM here. So let's go ahead and stick this stick of a RAM inside of here. I probably should have done that before I plugged in this cable, but that's fine. The RAM, most of the RAM you get these days, this is DDR3 RAM, I think. There's also DDR4 RAM, which most modern systems have. There's only one way to put it in. If you find yourself struggling to get it in, is because you're doing it wrong. Yeah. So let's open up these RAM slots here. So I'm gonna put this. If you notice it, this key, this has a little notch over there that is off center. So again, it's only gonna go in one way. Put it straight in here. Now, RAM is one of those components that they say especially to be careful with in terms of electrostatic discharge, or ESD. So let's go ahead and plug this guy in. Right. And there are two clips on the side here. Once those two clips are in place, you should be fine. I think we're okay there. I don't know why I'm waffling about so much about the RAM. Okay, cool. So anything else missing, guys? How would we know that this
hard drive or we don't?
No, we don't need a hard drive. Don't need a hard drive. That's optional, but we don't. I mean, I have hard drives here. Yeah. Or had hard drives here. So this for example is a laptop hard drive. You notice this plug here. That's the data port. That is the same type of plug that you see over here. So there's a SATA cable that goes between here, and over here you have SATA power connectors that plug in here. Again, most cables on computers, they only go in one way. Okay, so the missing component we have here is output. We have no way of telling whether or not this computer works unless, of course, we plug a monitor in. So I have a monitor over here, old school VGA. Go ahead and plug that guy in. I mean, blah, blah, again, obviously, it only goes in one way. All right.
Question, what happens if you remove the battery on board the board?
Nothing happens. They call this
It'll start
RTC battery, or the real-time clock battery. Back in the day, it was used essentially to keep the time on the computer. And even back then and now, it's used to keep certain settings that you set in the BIOS, for example, the boot order, the storage configuration, RAM speed, user settings like that. You can store. It uses this battery to store that because there's no permanent storage on the board. Yeah, all of the storage on the board requires power to continue to keep the data. So nothing will. The answer is nothing will happen if you change the battery. If you remove the battery, it will stop. It will just give you an error. So we have output here, we have power here, we have CPU power over here, we have our fan cable here, we have RAM, and this constitutes the basics required for turning on the system. Can anyone guess how we turn the system on?
Use a jumper on pin 5 and 14.
5 and 14. Sorry, we don't have that many pins, but yeah, you have the right spirit. So essentially, the power switch creates a short between two pins on the board. So the power switch is just two is connected to two wires that snake all the way down to this part here, and that's connected to two pins over here. So you guys aren't going to be able to see it because I'm not able to do a quick zoom here. But what I am going to do is locate the power switch, which would be these two pins over here, and I'm just going to create a short between them like so. And we see the power supply has started up, the CPU fan has started up, and this is a computer running on my desk. And I got this part is a little bit harder. We have the monitor plugged in here, and it's saying no boot device because obviously, as Richard pointed out, we have no hard drive hooked into this. So this is a good way to what they call bench test a computer. You eliminate all the other possibilities. When you get down to this level and you see that the monitor is working well, you know, well, it's not shorting against the case, then the standoffs are in the right place, there's proper grounding, and so on. So that is starting a computer, and as you can see, we did this in a couple of minutes while talking, while on video, all that drama. So it's pretty easy. It's not that hard. You could just consult Dr. YouTube to figure out how it goes. So inside here, just watching all the nice delicious components inside of that power supply. Okay, so there's no off switch. I can't repeat the trick to actually, I don't know if I can repeat the trick to turn it off, but I'll not try that right now. But I have a handy switch on the back of the power supply that I can use to take it off. So let me get this stuff out of the way for the moment. Right. These plugs can be a little bit difficult to pull out. You just wiggle it side to side. Right. So unlike your typical USB port, these things could only go in one way. When everyone knows there are two possible ways to get a USB stick into a USB port. All right, so we'll put this power supply out of the way. So actually, I'll leave it here for the moment. So what would you do if it didn't start up in that instance, right? If you had a spare CPU, you could replace the CPU and you could change the CPU, provided there's a compatible CPU for the motherboard, just check online. You could change the RAM, obviously, if you have no spare parts. But if you have a suspicion around the power supply, especially if it's a very cheap power supply, then you want to be able to tell whether or not the power supply is working, right? So one easy way to tell whether or not a power supply is working, is to use a nice little multimeter. So let me go through this multimeter guy here.
What about licking it? Could lick it?
In my experience, licking would let you know that there is a current and give you an estimate as to how much current, but it is not too good in the voltage department. So it'll tell you if it gets in 10 amps, in which case you're dead, or but it wouldn't tell you the voltage. All right, so this here is this is upside down. Okay, maybe I should do it like this. Yeah, that's why I did that. So this is a multimeter. Multimeter is used to measure various metrics around power and current and electricity. The main thing this guy is going to measure. Main things it's going to measure would be voltage. Well, voltage and resistance. There are two types of power, as mentioned previously. There's DC power and there's AC power. There's alternating current, that's when the waveform moves like that. And there's DC current where it just goes in one line like that, or in like up square waves kind of thing, depending on if you have some kind of conduit. So anyway, Chris, you're probably laughing at me. Okay, so this section here is for measuring AC voltage. This is the power coming from your wall. And this section here is used for measuring DC voltage or direct current voltage. This green section over here is used for measuring ohms, right? This here is for measuring current, AC current. Yeah, I probably mixed up some things there. Anyway, DC voltage, AC voltage, amps here. AC, this here is actually direct current amps over here. And this here is for testing continuity, or whether there's a circuit between two things. So let's take a look at some of the things here. So let's try the simplest thing we have here, which is the continuity or canary, as we all like to call it. So what this tells you is whether there's a circuit between 2 points. This multimeter is attached to these two oh my God, what do they call it? Probes. These two probes are positive probe and a negative probe, and essentially it's going to beep when it detects that there's a circuit between this side and this side, right? So if you join these two here, you hear the beep there, and you see a number there, and that means that there is in fact a circuit. So let's say you had some wire that you wanted to test, and you wanted to see whether the wire was broken in some way. You could hold the wire and, oh my God, sorry, I don't have a thumb. This is not going to, yeah. So you can hear the little beep there, meaning that this wire is not broken, and it's fine. There's no problem with this wire, right? Here's another example. I made this these alligator clips. I just bought the clips and then soldered them on to the wire here. So I could plug this in here, plug this in here. Oh my God, I need an extra thumb. And this is beeping as well. Right? So that is the basic test for continuity. In terms of mainboard diagnostics, that is super useful. The diode mode as well is super useful for that. All right. Next thing would be testing DC voltage. So if you were to take a normal battery like this is a AA battery. AA batteries are typically about 1.2 volts. So we want to check the voltage on this battery here. So again, sorry, but I don't really have many thumbs available. So I'm going to put this guy over. First, I'm going to put it over here because I'm expecting less than 2 volts. I'll put it on the number 2 here. I'll put this guy on the negative end of the battery, and I'll put this guy on the positive end of the battery, and we can see that this battery has a voltage of 1.3 volts. Generally speaking, the brand name batteries generally come with a higher voltage than the cheaper stuff. This is not actually a good way to test a battery. You actually have to have a battery on the load to be able to test the voltage properly. So I've shown you the basics of a multimeter. Let's show you guys how we can test this here power supply. So again, in the spirit of eliminating all other possibilities, making things as simple as possible, we want to eliminate the possibility that the plug itself is at fault here, right? That the power coming from your house is insufficient or under voltage or over voltage or something of that nature causing the issue. So what we're gonna do here, and please call my wife if I happen to fall off my chair during this demonstration, but we're gonna be playing with some live power here. So I am going to put my multimeter into AC voltage mode here. I expect no more than 200 volts because this is Trinidad and Tobago. This is not the UK. In the UK, they expect 200 volts. So you guys are probably going to be hard pressed to see what's written there. No, you're absolutely not going to see what's written there. But there are three holes here corresponding to the 3 plugs that go in usually. This one here is neutral. This one here is live, and this one here is ground. So what I'm going to do is double check. Yes, I'm checking AC voltage 200. I'm gonna stick here and hope to God that I don't die. Put that guy into ground there, not yet dead. Let's see what we expect. What do we expect to get here? What sort of reading we expect to get here? Anybody?
120 volts.
All right, let's stick him in there. Let's see. All right. So it's actually about 110 volts, not 120. Right. So that's us testing this power supply right here. So as we're talking about voltage on power supplies and so on, this is a pretty bulky power supply. It's typical size for a computer desktop. Laptops and so on, they have power supplies as well, but it's in the power strip, right? So again, but it's the same function that it serves, which is to take AC voltage and convert it into DC voltage, giving the computer 12 volts, 5 volts, and 3.3 volts. Wow, I didn't I should have advanced these slides. Sorry about that. Doesn't even matter, right? So the nice thing about your laptop power supplies is that they can actually handle 220 volts, provided you have a physically compatible plug. So you can go to the UK and use the same laptop over there. On this power supply, I think I can switch between 115 volts and probably 220 volts, but I'm not gonna bother to do that right now. So this being the main guy who provides power to the motherboard, we want to test this guy. So if you look at the presentation, the power supply pin layout over there, you'll see I have a notch over here which corresponds to this notch over here. I'm not sure if you guys will be able to see my mouse, right? So therefore pin is my pointy thing. Pin 1 is going to be over here, and he is expected to be pushing 3.3 volts. Pin 13 is over here and is also supposed to be pushing 3.3 volts. Over here, we have pin 11. Pin 11 is supposed to push 12 volts. Yes, 12 volts. You'll notice that they have colors on them, so that can also help guide you. So remember, pin 11 is yellow on that diagram here, and it's also yellow over here, right? So let's go ahead and start sticking our multimeter into things. So now this is not what they call an auto-ranging multimeter, so I have to specify the upper limit of the voltage that we expect. So I expect no more than 20 volts to be coming through here. If more than 20 volts comes through, there's something called a thermo fuse, I think it is. But the fuses on these guys, they kind of operate. A fuse is essentially a thing that protects your electrical components from being fried by too much power. What it does is that when too much power comes in, it will get hot. And when that fuse gets hot, it loses conductivity. So as you overpower it, the fuse would lose conductivity and stop supplying power to the rest of the board, and it would just start working again once it cools down after a while. Kind of cool. But I found that out after blowing one of my other multimeters. Okay, so let's go ahead and test this guy. Again, this is not going to be difficult because I only have, well, essentially 1.5 thumbs. So what we want to do, you always want to measure voltage across ground, from the positive end to ground, right? So we have a number of ground pins here. You can see all the black ground wires going to the respective pins here. So let's pick somewhere for ground. But you're not going to get anything here. So if I were to plug in into pin 3 here, this is going to be difficult, and then plug in over here where I should expect to get 3.3 volts, but obviously you're not seeing anything. Why? Why aren't we seeing anything? Why are we getting 0 volts here? Anybody?
There's no circuit with our ground.
Nope.
The CPU power supply off.
That is correct. So let's turn this power supply on. Has it come on? It hasn't come on yet, right?
Oh,
So how we turning this guy on?
make a bug and wait for somebody to deal with it.
All right, so generally this guy is plugged into the motherboard, and the motherboard via the power switch tells the power supply when to turn on. So if you look at pin 16 on the diagram, it's labeled PS on, that stands for power supply on. Essentially, if you create a short circuit between PS on, pin 16 and any ground pin, you're going to send a signal to this power supply telling it to come on. So let's go ahead and do that. Again, we're playing with real voltage here, but not really real voltage. This is DC, 12 volts. Just make sure you're going to use this nice little non-insulated paper clip to do this job. This is perfectly safe. I assure you, I haven't died yet. Right, so this is pin 16. That's a notch on the right-hand side. Pin 16 is 4 down from the right. 1, 2, 3, 4. Let's put that in there. And any ground, so any black guy, so I could plug them into 15, 17, or 18. So let's try to see where we go. Put that guy inside of there, and nothing happens. Why? Well, I have this switch off. Wait, hold on.
You have wireless electricity by you?
Yeah, so maybe I should turn this, I should plug this this thing in, right? So let's get that plug back into play here. Plug this guy here. Right, he hasn't come on yet, despite the fact that the switch is in the on position. Let me try this here again. Pin 16, which is 4 from the top. 1, 2, 3, 4. And plug the other guy into ground, which could be any of the following 2 guys. And we see the power supply has come on. Right? Again, if I disappear from the viewport here, is because I'm dead or dying. Please contact my wife. Julian should have my contact details. Should be on Bamboo as well. So let's go ahead and test some of these guys out. Right?
If ground is ground, why have so many ground options?
Ground? Oh, brown is not ground. Black is
No,
ground.
ground. If ground
Yeah,
is
why
ground.
are there so many ground options? I don't know. Parisha, if you want to answer that, you could take a try. I have no idea. I think if you do not provide enough ground, then you run the risk of having a short circuit. So you have everything has to complete a circuit. So if you have too much power going in, there are not enough ability for it to go back to ground, then you're gonna have a short circuit, you're gonna have a fire, and your key's gonna catch fire and bad things.
Yeah, that's interesting. And I thought about that when you first asked the question that there were different circuits there, hence the need for different grounds. While that might be true,
well, ground is common, huh? Ground
Yeah.
is common. So it means that if I did a continuity test between pin 3 and pin 17, I would hear a beep because ground is connected.
Mm-hmm.
All of the ground pins are connected.
Okay.
Yeah?
That's good.
All right, so let's go ahead. These guys don't stay in. So I need to find a ground pin that I can plug this guy into. I don't think I should be brushing that guy like that. So that is, so let's say, so ground 15, pin 15 is clear. I don't think I want to put him there. All right, let's try pin 3 here for ground, from a ground. So I practiced this, but the last time I practiced this, it was with two thumbs, not one. So let's go ahead. Pin 1, what's the voltage we expect there? Anybody? I can't see the diagram.
3 volts.
3.3 volts. Let's see what we get. Yeah, 3.32 volts. Yep, within the margin of error. Pin 2, we should expect the same. Yep. Since you're already in the area, let's check pin 13. Yep. And pin 14 is supposed to be something called minus 12 volts. This is minus 11.42. I am not certain. I guess the polarity changes there. I don't know what that means really in real terms. We're supposed to get 5 volts coming from pin 4. So, oh gosh, you guys not seeing this. Pin 4, put that there. Yeah, so we have about 5 volts here. Margin of error. This guy is 0 volts here. This is ground. 5 volts, etc., etc., etc. These 3 guys on the bottom here coming from these red wires supposed to be 5 volts as well, right? So that I wonder what this pin 9 is. That's 4 from the bottom. This purple guy. I guess he gives me 5 volts, but he's that VSB means something, but I'm not sure what it means. But yeah, so you would go through each of the 24 pins and verify that it shows the right voltage. So if you were to look at a 3.3 volt pin and you got 5 volts, or you got 12 volts worth, then that means that something is wrong. So there we have it with this power supply. Another way to test to brute force test this thing is to like pull out a fan and see if it works. So I have this this gonky old fan here that I'm gonna plug in here. This is called a Molex connector. Old timey computer hard drives used to use these connectors. Oh no.
Are all power supplies the same configuration?
In terms of
The pins are in the
Yes.
same order and color and well,
Yes.
not color, but order and what voltage?
yes, they are. So ATX power supplies are all in a standard configuration, and all ATX compatible motherboards expect the same configuration. Very standard. So you can buy a power supply for any desktop computer, and it should be more or less the same. The only power supplies, in my experience, that are different would be Dell, because they seem to like to have proprietary power supplies even in their desktop computers. All right. So yeah. So we were talking about these Molex connectors, and we have this nice little fan here. So let's go ahead. Make sure this fan is not connected to something that will kill us. And give him some power. Check it out, right? So we have our fan working there. I didn't actually show that on the camera. So I'll go ahead, 4 pins there, 4 pins here. The red ones we know is 12 volts. We can actually test that. We won't bother to. Yeah. So we have a fan working here. So let's look at how fans generally work here. All right. So with most computer case fans, what you have a side with a label, and you have a side without a label, right? The side with the label generally indicates the direction of airflow. So in this case, this fan with this label here, I'm not sure what's the best way here, means that the air is going to go in this direction, right? You guys can see where my screwdriver is going. The air is going to be sucked up and pushed out from here to there, right? So this is the back of the fan here. So let's take a look at the back of the fan here. So do I have a fan diagram? Yeah, hey, look, I have a fan diagram here, right? So if you notice here, this is more or less the same kind of thing here. You have, so if you might remember some of your primary school science experiments where you take a nail and you wrap a piece of wire around it tightly and then apply current to the wire. The nail itself becomes magnetic. It's called an electromagnet. That's essentially how fans work. So you could see a tightly coiled wires around here, and what happens, and the fan is attached around this area here. So the rest of the fan is attached around this area or something like that. But essentially what happens is that these magnets change polarity very, very rapidly. Sorry, let me switch my screen so you can see that a little bit clearer. It doesn't want to change just now. Yeah, that's fine. Right. So these guys these are just magnets, and they change polarity. All right, thank you. And they change polarity rapidly. So if you know if the north side of a magnet is in contact with the north side of another magnet, it's going to have a repelling effect. So what happens is, if this is in the north configuration and this magnet is in the north configuration, it's going to be forced to go in that direction to the next side, which invitingly has a south magnet waiting for the north magnet, and so on and so forth. And it's going to keep switching polarity all the time, right through, around and around. And if you want the fan to go faster, you just switch the polarity a lot faster. I don't know if I explained that badly, but that's fine.
That's the same thing for like big fans or just computer fans?
I think so. You know what? I think I'll open up my fan sometime soon and check it out, and I'll let you know.
All right.
But that is something we could do. All right. Whew. I almost stuck my finger inside it. So actually I needed this fan for a reason, because what we're gonna do next, let's see. let's see what the next topic is. What we're going to do next is do some soldering. So most of the problems, I want to show you something with some of these with computers, right? If you notice this power, so this, let me switch again. Let's hope it comes in a little faster this time. Hang on 1 second. Let me see if I can get my thing to switch. All right, hang on 1 second. Let's go take a peek behind the curtain there. All right, and we should be good to go again. Let's see what you guys are seeing. All right, okay, cool. All right, so this is your normal computer main board, right? If one of the things I noticed is that like the majority of the components on a computer are kind of devoted to power and power management, and most of the problems that you have with electronics is related to power management for some reason or the other. Chips or the integrated circuits, the ICs, don't generally go bad, but what goes bad quite often would be diodes, fuses, capacitors, and things of that nature. The power components on a computer motherboard are what generally goes bad. And in the case of water damage, if water were to fall on your components, what usually happens is that you get a little bit of corrosion on your components. So, for example, if you have capacitors or something, and you have corrosion there, then the capacitor might short the ground, which would cause some other component to fail, which would cause the computer to not start up. So again, almost everything related to these computer electronic devices in terms of failure is power related. Everything is power related. And I was saying this because we want to look at one of the most common issues that you have inside of any electronic device in terms of something that's failing would be a broken connection, right? Again, power related, it's a broken connection, right? And you might want to fix your broken connection. So that is where soldering comes in handy. So quite usefully, I have the remains of an electric pencil sharpener, and I'm gonna grab this guy for practice. So I'll just grab this guy. So let's say the problem with this electric pencil sharpener was that there was a break in connectivity inside of this wire, right? And you needed to replace this wire, which is something that you can very easily end up having to do. So let me go ahead and show you what's happening here. So let's say we have this broken wire. These guys straight away, and let's get this guy here. So this is the wire we're working with, and let's say we wanted to join these two wires back together, right? I mean, you could just use a knife, peel off the insulation on either end, kind of wrap it up and tape it up with some tape, and that's fine. I mean, honestly, that's fine for many low voltage kinds of situations. But if you want to get a little bit more fancy, a little bit more technical, you could use soldering. Soldering is like welding. And this I haven't shown you my soldering iron. So this guy here. So this is my soldering iron. It essentially takes power and converts it to heat at the end here. Don't touch it. It's very, very hot, and it's used to melt this conductive wire. This solder wire itself has a very low melting point, and it melts very easily when in contact with the heat. Right. So let's practice this out a little bit. I put the fan here because soldering generates a certain amount of dangerous fumes that you don't really want to get in contact with. So I know which direction this fan is blowing. So I'll just put that somewhere over here. I just touched it, and that's fine. I'm not yet dead. Right, I'll put that fan there out of the way, and I'll get my soldering iron into the viewport over here. Right. So one of the things I realized that we needed, so I recommend a soldering iron with a rating of 65 watts. It keeps the heat a lot better, a lot easier to work with, and so on. Soldering wire, very, very cheap, like $8 or something like that. I bought this fancy guy here called Helping Hands. Comes with a nice little magnifying glass and these clips here to hold things together. It's not nice not having fingers, right? And there are a couple other optional things there. I like to have an old DVD drive here to use as my surface so that I don't end up burning my desk here. So I'll just put that there. And let's say the task here is to join these two pieces of wire. Fortunately, I have wire strippers as well. This is so cool. I'm just gonna, oh my God, this is so much nicer than a pair of pliers. You wouldn't believe. Much fun. You feel like stripping wires all day. So just do that and bam, you have a nice piece of stripped wire here. Yeah, there you go. Come, focus. Okay, it's not gonna focus, but you get the idea. Oh my God, I don't have fingers. All right, so let's go ahead and strip this other part here, right? So we have this wire strip, and now we're gonna do the same, give the same treatment to this other guy here. Yeah. If you're at home, of course, you're not limited to using your fingers. You're allowed to use your thumbs. Right. So now I have my two pieces of wire, and I want to join these guys up. So what I am going to do first, I'm going to what they call tin my my soldering iron. Tin, they call it tinning because the solder is essentially tin and our good old friendly neighborhood lead. Again, that's why we have our fans running here right now. So I'm just gonna touch the tip here to the soldering iron, and having a little bit of the solder on the tip kind of aids with the heat transfer between the soldering iron and the thing that you're trying to solder. So I'll just apply a little bit of that solder. Apply a little bit of that solder to this this wire here. I don't think I'm very successful there, but here's what I'm going to do. I'm going to join these two guys together now. I don't know if this, I've tried before with this magnifying glass and this setup. I don't know if it's gonna work well in terms of the camera and so on. So I have that end plugged in, and let's try to join them to this guy here. Right. So I can get these guys close together. Now, of course, you could do this by hand, but again, I just find this stuff pretty cool. Right, and I'm going to take some of my wire, and essentially the soldering wire is kind of attracted to the heat. So where there's heat, the soldering wire is going to follow. So let's see how well we can make a connection between these two guys here. I'm going to melt this guy a little bit here. Yeah, you guys could probably see better than me because you have the magnifying glass. This is a very, very poor soldering thing. It's something I need to practice, but it will do for most intents and purposes. Solder, of course, it gets hard very, very quickly. That's very hard now, and you can actually touch it there. And that's it. These two wires are now joined, right? What I missed there, what I haven't shown you, is that typically you don't want to leave your wires exposed in that way. You kind of want to have some insulation around that wire. So there's something, what do you call this? Sleeves I can't remember what they call it, but these sleeves is essentially heat shrink sleeves, right? So essentially, this is a tube that you could slip over the wire. So I cut enough here, and once you apply heat to it, it's gonna shrink and close in over the thing you soldered here. So I'm gonna so I should have actually had this over my wire before I started the soldering process. And because I did such a bad and terrible job of soldering there, so this guy is supposed to go over there, but I'll just demonstrate it anyway. And you take a lighter.
And because the wire wasn't straight.
Actually, well, I mean, yeah, the wire wasn't straight, but I did a terrible job. Yeah, that's right. So let's go ahead, take this guy, push him through, and let's try him from the other end. See if that is a little bit better. I swear I would get this working if I had extra thumbs. Okay, kind of force that in there. I may have broken the connection. That's not a problem. You could always test it with the oh, I think my fingers bleeding now. All right, so we have oh, you guys were off camera all the time. Sorry about that. All right, I'll just remove this guy here. So what I'm going to do here, I'm just going to hope that the breeze isn't too hard and just give this guy some flame. And you'll notice the heat shrink is kind of shrinking. So this heat shrink is actually made for thicker wire. So it's not going to work as well with this thin wire. But at this point in time, you have a nice connected piece of wire. And this stuff, again, I didn't do any electronics training, any formal electronics training. I am just learning this as I go, and yet I'm able to apply what I know to fixing real stuff. Case in point, this nice little timer thing here, because my daughter gives a lot of trouble to eat. We set up a timer for her, and every 2 minutes she has to take another mouthful of food, etc. She has problems focusing on what she's doing as well. So she tends to take it to the shower, and we tell her, okay, 5 minutes max in the shower, and set the timer so you'll know when to come out. As told, she walked into the shower with it, put it on the side, splash around, play with her ducks and so on, wet the timer, mash it up. So it stopped working. What I did was I took it apart. I took it apart and I used some alcohol and just essentially cleaned the contacts. Put it back together again. It worked, and it refused to turn off for some reason or the other. If you think about it, the reason it stopped, it refused to turn off was because the switch here, two of the wires were shortened. They were touching each other essentially, and causing it to be on all of the time and not be able to be taken off. So what I did, I opened it back up again and provided some additional heat insulation by the heat shrink tubing, and that was able to solve the problem. So that's just a little small timer thing that I was able to fix using some of these skills. Now I want to move on to main boards. I want to move on to motherboards. I want to start fixing laptops and stuff because I think it's pretty interesting. But you don't have to. What I want you to come away with is that it's not that difficult. You could just spend a little bit of time figuring it out and looking at YouTube and so on, and learning some of these basics. It's not that hard. Most of us are able to do it, and the equipment itself is not expensive. This soldering iron, for example, might have been 130. The multimeter would have been about the same thing. This DVD drive here that I use is free. Power supplies, computer parts keep finding their way to me. So you have things that you could play with, and I encourage you to get involved in repair, even for your own devices or other people's devices. It'll help a lot of people in these times. As a final addendum to this this power hour, what I'm going to do is take you behind the scenes a little bit very briefly and show you my OBS setup so that you might be able to check it out yourself. So very quickly, I'm going to do that. So I'll share my OBS screen itself. So this is my OBS screen here, and I can switch between different views and so on. So this comes from 3 different inputs here. Here are my sources. One is my Nook screen, actually part of my Nook screen. I have here the Nook Logitech camera. That's this guy here who's pointing down at my desk, and I kind of put him in an upside down and kind of zoomed in mode. And this face camera here, this was actually kind of roundabout. What I did was I remoted into my Surface laptop, which is right underneath here. Actually, that's this guy that you see over here. And so this is the remoted in Surface computer, and I have the camera app running here. And I have that window as an input source on my OBS screen here. And I could switch between different layouts and so on to go between them. So this has been the Canon TV, Justin, if the LCD panel is broken. I can't fix that. Okay, this has been another episode of Ryan Minutia.
I have a question. That redacted power slide, we're going to see the unredacted one, like where the purple couple from, I don't know, all these questions.
Well, that came from this, essentially. Sorry, this. There was just a bunch of bullet points I had. So I had most of this stuff there. It would have been expanded since then, obviously. Yeah. I'm not in control of my legal team. They kind of I like to limit my liability.
Sure.
Yeah.
On the OBS front end, you can check out something called NDX. It allows you to NDX. It allows you to stream stuff in your home network to your OBS setup, so that you don't have to remote into your machine.
Yeah.
You just stream it.
Yeah, Gian had told me about
sorry, NDI. I'm saying NDX. NDI.
Yeah, Gian had told me about using my phone. But I think he had told me that he needed some kind of sketchy app, and I didn't want to go down that route, but there seems to be some open source things that you could probably use. So yeah, that's a good tip. A top tip.
A very cool presentation.
Really, really cool. Could we, if there are no questions, I just want to kill the recording. So let me wait. Are there any more questions?
Let me close the recording with the music so it finishes nice when you're ready.
Nice. Go ahead. All right, nice. I have to remember to